Okay, the binomial theorem deals with a binomial raised to a power. So before we start talking about what the binomial theorem is, I have 5 binomials raised to a power that I would like you to go ahead and find for me. Okay, now if you find x plus 1 squared, that can help you with x plus 1 cubed. And if you have x plus 1 cubed, that will help you with x plus 1 to the 4th, right? So go ahead and take a couple minutes and find me each of these binomials to a power. Work together. Make sure, check with your neighbor. Are they getting the same thing? What's anything to the 0 power? Okay. Nathan, what's x plus 1 to the 1st? Jack, what's x plus 1 the quantity squared?
X plus 1. Oh, squared?
Yeah.
X squared plus 2x.
Madeline, what do you have for x plus 1 the quantity cubed?
X cubed plus 3x squared plus 3x plus 1.
And if we take that times x plus 1 for x plus 1 to the 4th, Kelly, what do we get?
X to the 4th plus 4x to the 3rd plus 6x to the 2nd plus 3x plus 1.
But did you say 3x right here?
4x.
Oh, okay. That's plus. I think I'm a little off here. Okay. Do you see a pattern? What's the pattern? It's part of that triangle. Pascal's triangle. If we look at the coefficients, 1, 1, 1, 1, 2, 1, 1, 331, 14641, we have what is called Pascal's triangle. Okay. Let's talk about some patterns with Pascal's triangle. Okay. 3 plus 3 is 6. 3 plus 1 is 4. 6 plus 4 is 10. Etc., etc. So if we were going to write the next row, what would it be? Just everybody say it out loud.
1, 15, 20, 6.
Good. Okay. If you noticed when you walked in the room, I have some Pascal triangle Christmas trees on the hallway. Anybody notice this? No? Okay. In math club, we colored some Pascal triangle Christmas trees. Okay. Pascal's triangle is used for a lot of different things. Okay, there's a lot of applications that we can use it for, but one in particular is that Pascal's triangle describes the coefficients when you expand x plus y to the nth power. Okay, those coefficients, or these numbers, like if I were to expand x plus y to the 5th power, then our coefficients would be 1, 5, 10, 10, 5, 1. Okay, we could just go to that respective row and grab Pascal's triangle. Now, in your warm-up, I had you kind of do it step by step by step, right? But how much work was it just to get x plus 1 to the 4th? I mean, it took some time, right? Well, what if I asked you for x plus 1 to the 8th power? Okay, that's a lot of tedious work to try to multiply a binomial 7 times over and over and over and over, okay? Well, instead, we can just go to the row of Pascal's triangle and grab 1, 8, blah, 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 blah. Now, am I asking you to memorize Pascal's triangle? You do not need to memorize and write out Pascal's triangle every time you want to multiply out a binomial. Okay, first of all, that's also tedious, right? Well, what if we have coefficients with like that x and y? How does that affect the coefficients when we expand it out? Okay, so we have something called the binomial theorem. It uses Pascal's triangle, and I'll show you how here in a moment. But something that you talked about in Algebra 2 is this right here. Okay, if we take x plus y to the nth power, then we're going to sum up a bunch of terms. Okay? We're going to sum up a bunch of terms that look like this. N combinations of r, where x is raised to the n minus r power and y is raised to the r power. Write it down, because I know it looks strange, and then we'll talk through what it all means. So we just got done with our sequences and series. You know that the sigma means sum it up, right? So we're going to start by plugging in 0, and then we're going to add when we plug in 1, and then we're going to add when we plug in 2, okay? Whatever n is, like if we have x plus y to the 5th or x plus y to the 6th, that's where we're going to start right here with our combinations, okay? n combinations of 0, and then our next term is going to be n combinations of 1, and then our next term n combinations of 2. Okay? X is always going to be, we're going to start with this first variable being raised to the, it's going to end up being raised to the n power. And then every time we add a term, this first variable raised to a power is going to go down in power. Okay? Every time we add a variable, this y is going to go up in power. Okay? And I know I'm talking about it and you're not really seeing it happen right now. So when we get into our first example, this will make a little bit more sense. Okay? But each term is going to look like this. Okay? Now you don't need to write this down, but this n combinations of r, that's called our binomial coefficient. Okay, well, we just got done talking about how Pascal's triangle are the coefficients for our binomial. And now I'm telling you n combinations of r is our coefficient. Fun fact. Pascal's triangle is the same as these coefficients. Okay, so each row in Pascal's triangle is a combination. So this row right here, 3 combinations of 0, 3 combinations of 1, 3 combinations of 2, 3 combinations of 3 is the same as 1, 3, 3, 1. So Pascal's triangle and this little summation right here with the combination, it's the same thing. Okay, so instead of having to like write out Pascal's triangle all the way out to like 15 rows, we can just understand that that each row is a sequence of combinations. Okay. All right, so let's go ahead and put this to use. You already know what a combination is. We're going to skip that slide. Go ahead and write this down. We are going to take 2x minus 3 and raise it to the 4th power. Okay. Now, in your warm-up, or your combination warm-up, I had you take x plus 1 to the 4th power. And that really wasn't so bad because there weren't coefficients. It was just 1x plus 1. Okay. But when you multiply over and over and over in terms of a binomial times a binomial, and then that times another binomial, and then that times another binomial, there's a lot of room for error, right? Whether mismultiplying, misadding, something like that. So this can at least alleviate some of that, and it's going to take less time. All right? So our binomial theorem. N is 4. Okay? 2x is grouped together as our first term. Negative 3 would be our second term. Okay? So what we're going to do, since n is 4, we're going to start with 4 combinations of 0. Okay. 2x is that first term. It gets raised to the n power, and then negative 3 gets raised to the 0 power. We are always going to start out with n combinations of 0, our first variable to the n, our second variable to the 0. Then we're just going to adjust and account for our pattern as we go. Okay? So then our next term is going to be 4 combinations of 1. But now 2x is going to decrease in power, and negative 3 will increase in power. Going back to you, Katie. Then for our next term, 4 combinations of 2. 2x will now be raised to the second power. Negative 3 will be raised to the second power. Decrease the first power, increase the second power. Okay. Our next term will be 4 combinations of 3. 2x will be raised to the 3 power. Oops, nope. What's 2x raised to?
First.
The first. Negative 3 is raised to the third. And then our last term would be 4 combinations of 4. This is how we know it's the last term, because we're at n combinations of n. These two match. 2x is now raised to the 0 power, and negative 3 is raised to the 4th power. That's a 4. Okay? Before we actually start calculating all of this out, let's look for some patterns. What do you notice about each pair of exponents? They add up to 4, which is n. That should happen every time. Okay? What exponent does this number match with every time? Okay? These exponents right here are always matching. Something to kind of think about if I were to ask you for a term instead of the entire expansion. Okay? Now, we're going to, I need to see you write this down in your work on Friday. Okay? This next step I'm going to do, some of you will probably do in your calculators, but I want to just at least show you where the numbers are coming from. So help me out. What is 4 combinations of 0? 1. So we have 1 times 2x to the 4th would be 16x to the 4th, and negative 3 to the 0 is 1. So those 3 numbers get multiplied to 16x to the 4th, and that's our first term. Then we have our second term. 4 combinations of 1 is 4. 2x cubed would be 8x cubed. And negative 3 to the first power is negative 3. Those 3 numbers all get multiplied together, which is negative 96 x cubed. There's our second term. All right, 4 combinations of 2. What is that? 6. 2x, the quantity squared, is the same as 4x squared. And then negative 9, the quantity, negative 3, the quantity squared is 9. So we're going to take 4 times x squared times 9, which is 216 x squared. If we were multiplying this out, like foiling terms together, I mean, these numbers aren't like crazy big, but they're big enough to where there's a lot of room for you to make some addition or multiplication errors. Okay. All right, our next term, 4 combinations of 3 is 4. 2x to the first power is just 2x. And then negative 3, the quantity cubed, careful, is negative 27. Those 3 values get multiplied together for our next term, which is negative 216 x. Okay. And then our last term, we have 4 combinations of 4 times 2x to the 0 times negative 3, the quantity to the 4th power. So we have 1 times 1 times 81. So our last term is 81. And without actually having to multiply any binomials together, we have 2x minus 3, the quantity to the 4th power. Okay. I know that I talked about it a lot, so it doesn't feel like we saved time, but we really did. What questions can I answer for you about this process? Okay, I have another example that I want you to set up. So I have x squared plus 4 cubed. What I want you to do is I just want you to set up the 4 terms and then stop. Okay. Set up the 4 terms and then stop. You have it written down, I encourage you to check with your neighbor. See if you have the same thing. Okay. Do your 4 terms match mine? Okay. What I wanted to talk about in this example, as we have it set up right here, okay, these exponents are adding up to 3. And once again, our second exponent matches the number in our combination. However, when we get this all multiplied out, that's not going to be the pattern anymore because we have that x squared raised to a power, okay? But at least when we set it up, we should see those patterns happening, okay? Now, on your test, if you do all of the rest in your calculator and write it down, I'm fine. I at least need to see this set up right here. And then if you want to say, all right, this is 1 times x to the 6th times 1. So we can just write x to the 6th. And this right here is 3 times x to the 4th times 4. Okay, we can do that calculation. That's 12x to the 4th. Okay? And then I know that this is 3 times x squared times 16. Right? What's 3 times 16? So we have 48x squared. And then we have 1 times 4 cubed. And 4 cubed is 64. So I'm okay with you not showing me that second step that we had in our first example. If you have the setup and then the answer, I'm pretty good with that. Okay? But I do want to see where your numbers are coming from, so at least write out the binomial theorem so I can see it. Okay? All right. For the last few minutes of class. Okay. Go ahead and write this down. We're going to talk about the sixth term of a plus 2b to the eighth. Before we talk about how to do this as a class, discuss at your table how you think, don't set it up, but just discuss at your table how you think we should set it up. 1, 2, 3, go.
Do the same thing we've been doing. The other one that makes all that difference.
This equation is similar to this.
Yeah. And then five.
Will you lay out all of the terms?
Yeah.
Or do 8 combinations of 6. And we need the one term.
From left to right. Yeah. Like
Do
we
8 combinations of 6
Yep.
time.
Do we need the entire expansion to be able to find this one term? Oh, no. Okay, I will never ask you to take a binomial to the 8th and give me all 9 terms. Okay, that's probably more than I want you to do. But I can ask you to find one term. Okay, so pod 4, tell me what you guys talked about at your discussion.
We were thinking that before we did it, so that it would be like choose 6 times a at the second times 2b at the sixth.
Okay, 8 choose 6 is what you were wanting to start with, correct? Okay. Did anybody have a different discussion at their table? What did you talk about?
We said that it would be 8 choose 5.
8 choose 5. Okay, I have an 8 choose 6 and an 8 choose 5.
Choose 5.
Oh, you're saying 5. Okay. Let's think about this. Okay, well, Ryan, why is he saying 8 choose 5? Okay, when we start off our expansions, we start off with n choose 0, right? So that is our first term, and then our second term is n choose 1, and then our third term is n choose 2. So since in this expansion we'd start off with 8 choose 0, our sixth term is actually going to have 8 combinations of 5 attached to it. Okay. Now, if we have 8 choose 5, five also goes where? With 2b. This tells you the exponent for 2b, which means a has what for an exponent? 3, because these two need to add up to be 8. Okay, so in your calculators, please find me 8 combinations of 5. It's what?
56.
It's 56. Okay, but don't forget that that 2 attached to b is being raised to the 5th power. What's 2 to the 5th? 32. So what is 32 times 56?
1,792.
Without having to multiply, we have a term.
Why did the
Do you answer your own question?
I was just wondering why the 32.
So if we take 32 times 56, we get this number. So I want just one coefficient for my term, so we need to multiply those together. All right, I'm going to have you set up this problem for me. So write it down so when you look back, you know what you did. But I want the coefficient for a to the 6th, b to the 5th. Go ahead and at your table, set up what you think it should be. Talk to each other at your table.
Yeah. So,
You have to multiply it out.
Right, we have this going on up here. We know that each term is set up by 11 combinations of something. 3a to a power, negative 2b to a power, right? What power needs to be on A? 6. What power needs to be on B? 5. So what combination should we have right here? 5, because it needs to match this second exponent. Okay? So we need 11 combinations of 5, 3 to the 6th, and negative 2 to the 5th, all multiplied together.
It would be 462 for 11, choose 5.
Okay?
And then it's 729 for 3 to the 6th.
Okay?
And then since we already know it's negative 32.
Okay? So let's all of that multiplied together.
Negative 10,777,536.
Now, I'm only asking for the coefficient. So notice how I did not write a to the 6th, b to the 5th. I only care about the coefficient. So I just multiplied those numbers together, and that is our coefficient for a to the 6th, b to the 5th. Okay? So make sure you read what they're asking you to find, whether it's a term. A term would be all of it, right, with the a's and b's. A coefficient would just be the number out in front. Okay, you have a book assignment, which needs to get done. It's very, very straightforward. Either expand this binomial, find the term, find the coefficient. Okay, exactly like what we did here in class. So make sure you get that done. Tomorrow, as I'm checking off homework, if there's some homework assignments you haven't shown me, make sure I see them this week. Okay?
Did you say we can turn this back into you?
If you don't want it, I'll take it.
So, like, this is.
Thank you.